Hello everyone, this is the video lecture of section 12.4 of Calculus 3, 2533, Math 2533. Today's topic is surface area. When a surface is given by a vector equation, you remember this? Section 10.5. In general, we need two parameter representation. If you write it this one as x coordinate equals f of uv, y coordinate is g of uv, z coordinate is h of uv, that would be parametric equation of the curve S. Or as it is, vector equation of the curve. For a line, for a curve, you need one parameter equation. For surface, because it's a two-dimensional object, you need two parameter equation, vector equation. So, your UV is living in some domain in abstract UV plane. For any given UV, you have a point. Position, this is a position vector of the point, corresponding to this UV value, right? Different UV value, different position points. If you collect them all, it'll form a surface, okay? So, when you're given this vector equation, we can consider some grid curve. For example, U0, V, C0, the first grid curve is obtained by fixing U value at U0, only let V varies. So that means x of U0V, z equals C of U0V. So U0 is a fixed constant. Alright? So it's a curve, right? So here U0 is fixed. So for this way, your graph is moving this way, in this case. So this is a parametric curve, isn't it? Right? So once you fix one variable, U value, only let V moves, it'll be forming a curve on the surface. Alright, this is a grid curve when one of the coordinate parameter value is fixed. Now we can consider tangent vector to this C1 grid curve, that is V derivative, right? V derivative and evaluate when V equals V0, all this function. Okay? Or in short, we want to write it R sub V, U0, V0. So here V derivative will be actually same as V partial derivative at U0, V0. V partial derivative of Y at U0, V0. And V partial derivative of Z, U0, V0. Okay, that would be tangent vector to the first grid curve. Likewise, you can consider this time you fix second parameter V value as fixed as V0. That would be x of UV0, y of UV0. Right? And then this partial, the tangent vector will be U derivative, evaluate f u equals U0 of this function. That will be R sub U partial at U0, V0. Which means round x, round u, round y, round u, Okay? Now, if R sub u cross product R sub v is not zero product, it's not zero vector, that means R sub u, R sub v are not collinear. They're not parallel. Okay? Cross product becomes zero when they have the angle between them 0 or 180. Parallel case. If they are not parallel, then cross product will be what? In this case, actually going through this way, right? Anyway, perpendicular to the tangent plane to the surface, right? Then it is normal, perpendicular. This is perpendicular to the tangent plane. All right. All right. Now we want to find the surface area of this one. First of all, let's consider the case where our domain D, perimeter domain D, is a rectangle case. So U and B, right? As usual, A to B, C to D, UV. From vector equation UV, let's say you're going some surface like this. Okay? Now, if you draw just like before, uniform division. Why this one is? Okay. If you subdivide this, the usual division, right? Let's say this is V, let's say here delta U equals B minus A over M, delta V equals D minus C over M, right? And then UI, the usual thing. A plus I times delta U, Vj is C plus J times delta V, all right? The usual partition, okay? Let's say that is Rj. This is subrectangle Ij corresponding to here Vj minus 1 and here Vj. Here Ui minus 1 and Ui. Ith subinterval cross product, direct product. Jth interval, ith one, jth one, this is Ij subrectangle. Okay? That grid lines will be, if you think about the image of these lines through this vector equation, that will be something like this. All right? Along the surface. Right? So let's say that Ij one will be going into here. Okay? So we want to find the area of Ij's patch of the surface and then add them up. Okay? All right. So this point Actually, I wrote it here ij, but anyway, it's not. Okay, this one was I and I plus 1, j and j plus 1. Fine. This is ij prime. This point will be pij. So O pij. So if you draw y, then this vector going into this OPIJ vector, okay, is exactly IVJ. Okay? Then, so again, we want to find the good approximate value of this area of IJ patch. Okay? How do we do that? If this delta U and delta V are very small, and this patch will be also very small, when you have a very small patch on a smooth surface and magnify, it'll almost look like a plane. Almost, you might not see a curvature. Just like in a great plane, you don't see any curvature on the plane. On Earth, even though Earth is sphere, because it is so large and the area you can see is so small compared to the entire size, you don't feel any curvature. Same thing. When delta U, delta V are very small, then this will be also small, and you don't feel much of a curvature. So what I'm trying to say is that if you magnify that region, it's almost planar, almost a planar, and this is Pij, corresponding to I and J. This will be, okay, so that that vector is R of Ui Vj, and then the origin is way down there, right? This will be R. The next one, I and I plus 1, which means Ui plus delta U Vj. And then another from origin down there. This is Ui Vj delta V. Okay? Then this will be almost a parallelogram. Okay? When delta U, delta V are very, very small, this will be almost a parallelogram. Okay? So we define this one as A vector. Vector A connecting this vector B. So your patch will be almost same as a parallelogram generated by this vector A connecting Pij and Pi plus 1j. This is Pij plus 1. Okay? The area of this, we call it the I surface is called S, then I'm going to call it Sij, the whole Ij patch. And the area of Ij patch of the surface will be very closely approximated by area of the parallelogram generated by A and B. Okay? You know that parallelogram generated by this vector A, vector B, the area is magnitude of A cross B, right? Because cross product is magnitude of A times magnitude of B times sine theta. That's the exact formula of the area. parallelogram. And then your A vector is what? R of, look at this, vector function ui plus delta u v j minus ui vj. So vj is fixed. So think about this one as a function of u. That is exactly u partial derivative of ui vj delta u, right? Linear approximation, remember? F of x plus delta x minus f of x equal to f prime of x delta x, remember? This comes from here, right? Linear approximation, just like that. V is fixed, so derivative will be u partial derivative. Likewise, vector B is R of ui vj plus delta v minus vj is also, now this time u is fixed, v is changing, so v partial derivative at ui vj times delta v. Okay, so you can take a look at figure 3 on page 869. Of course, it was exaggerated, right? Your ijth patch will be really, really small. So after you magnify it, this will be almost straight lines and almost parallelogram. The picture here was exaggerated when delta u and delta v are not as small. So for that, what do you have? If you do, so area of Sij, which was approximately this, right? Which is approximately what? R sub u ui vj cross R sub v ui vj delta u delta v, right? When you take cross product of this one and this one instead of A and B, so there are two-step approximation. So the total area of the entire surface should be, double summation. A of Si, this ij, which means this one, right? Sum of this approximate value of the area of the ij patch. So you have to put this. Which is delta A, area elements. In here, right? Here, delta A here, it's delta U, delta V. So this is double Riemann sum, right? This is approximated by this. Now, smaller the delta U and delta V, the better the approximation. If this one goes to 0, which means if m and n goes to infinity, this approximate value will be getting closer and closer to the true value. So, A of S is limit of m and n both going to infinity. All this will be double Riemann sum. The same thing, all right? You put right? That's precisely what? Limit of double Riemann sum, double integral. It's a double integral of this function. So it's a double integral of this function. R sub u cross product R sub v. R is this vector value function. It's a function of uv. This is double integral in terms of uv. Okay? That's the formula of surface area. Now, even though we started with a rectangular region for D, but it's okay to be, you can extend that one just like the previous section, 12.3. Okay? So, the first example here is find the area of the helicoid. U is between 0 and 1, and V runs 4 pi. Now you can, it's a spiral ramp, remember this one? U runs, this is a radius, a distance from the z-axis. U is from 0 to 1, all right? Now V give you direction. From V is the angle, right? From the positive x, positive y, V means, let's say V equals pi over 6. Then, when V runs from 0 to pi over 6, during that time, your xy coordinate is swinging, right, for given u. As V changes, this one is going up, right? It's a helix. When u is fixed, it is a helix. Given V, u is from 0 to 1 means this. So the width of the ramp is 1 unit. Okay? So you can think about this 1 unit length of the stick is rotating when you go around the axis, right? It's a spiral ramp. 4 pi means you're going to do twice. You go to 2 stories up. Okay? That's the shape. Now, in that case, how do we find the area? All right. Well, according to this, we have to find. By the way, this the graph is given at page 732. Chapter 9. I think chapter 9 6. 732, graph 4. You can go back and check. And then R sub u equals u partial. U partial, so it is 0. R sub v is v partial minus u sine v, u cosine v, and 1. And then you just take cross product. When you take cross product, you can see the detailed calculation. So in the end, you get sine v minus cosine v and u. All right? So this is tedious calculation. You go through it. All right? Then magnitude, here it is. Magnitude of that is magnitude is square root of this square, sine square v plus cosine square v will be just 1. And then u square, right? So you just have to integrate that, all right? So A of S, double integral of D. Now D is this. This is D, domain of the vector value function. This one, dA. So your domain of double integral is rectangle. So you can write it in iterative integral. V runs from 0 to 4 pi. U runs from 0 to 1. du and dv. All right? Now, you can write this one as, you can consider that constant 1 is your function of v. Separable function. So you can separate 1 dv. Now, this integral requires complicated trigonometric substitution. So instead of doing that, we'll just take, integral. We will just use integral table. So this is number 21 in the integral table of your textbook. I think a front page or the back cover. Yeah. Like this. You see this one? 21 on your textbook back page, number 21. That is this. Then you can write this one as, right. So anyway, this is 4 pi. And then it is u over 2 square root of 1 plus u squared. And then 1/2. And ln of u plus square root of 1 plus u squared. 0 to 1. Okay? So in the end, this is going to be 2 pi times the square root of 2 plus ln of 1 plus square root of 2. It's a simple calculation. You can do it. All right? Now, our example 2 is your example, textbook example 1 on page 869. Page 869. So what is it? Find the surface area sphere of radius A. All right? So this one is just a tedious calculation. All right? So I'm not going to do this one. So this is a doing assignment, as you can see in the lecture notes. And then the only thing you have to remember is instead of r, u, v, in this case, it's going to be phi theta. Okay? They say phi theta. Phi theta. We're using phi theta instead of u. So phi theta is our this one. And radius A, A cosine phi, no, A sine phi. Sine phi, cosine theta, A sine phi, sine theta, A cosine phi. In spherical coordinate, you have rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi. Here we just fix rho, fixed value as rho as A, because it is a sphere. This is a standard characterization of sphere. So your phi is between 0 and pi, theta is between 0 and 2 pi. So rectangular region in phi theta. So what you have to do is just, excuse me. So you have to calculate this one, and then you have to calculate another one. Instead of r sub u, r sub v, you have to do r sub phi, r sub theta, take cross product, and take magnitude, all right? And if you do that, you're gonna go through all these calculations, you get a squared sine phi. And then your surface area will be, from domain D, this one, okay, d phi, d theta, right? Oh, this is a squared comes out. Phi runs from 0 to pi, iterate integral, separable equation. Phi and 1 d theta. This is 2. This is 2 pi. That's why you get 4 pi radius squared. 4 pi r squared. Surface area of a sphere formula. Just proved. Okay, just prove it. But the details of this calculation, I refer you to the textbook. Okay? Now, for the rest of the section, sometimes your surface, quite often, is not given using vector equation or parametric equation, rather given as S is given as the graph of z equals f of xy. Okay? And your xy is in domain D. Right? Something like this. Domain D. This is D. This is your S. Okay? What if your S is given as a graph of a function of f of xy? Well, we can make a parametric equation out of this. How? We use x as parameter, y as a parameter, and okay, you could say the uv and uv. So r of xy as x and y f of x. Okay? Or you could say uv f of uv. Why do we, when u and x are equal and y and v are equal, why don't we just use x and y? Okay? So then r sub x, we're going to use the same formula, right? The formula was this. I'm going to write it here. The surface area was r sub u cross r sub v, magnitude of dA, right? So r sub x, f sub x, r sub v, 0, 1, f sub y, right? So cross product. The cross product, when you do this I, j, k, 1, 0, f sub x, 0, 1, f sub y, partial derivative, then you are going to get, actually, minus f sub x, minus f sub y, and 1. Okay? So, the magnitude of this one is square root of 1 plus f sub x squared, f sub y squared. Okay? That's why your area of surface is double integral of this function, 1 plus f sub x squared, f sub y squared, square root of this dA. When your surface is given by this z equals f of xy. Okay? We just apply the same formula to this special case. We just make a parameterization. X equals x, y equals y, and z equals f of xy. So x, y plays the role of u and v. Okay? That's how you got this formula. Now, if your surface is given as not as like this, let's say, y equals g of x z, then you can do the same thing. Then what do? X equals x, z equals z, and y equals g of x z, right? Y equals g of x z, and z equals z. Now, x, z, are playing the role of uv in this case. So then you have to do r sub. So your r, so r x z is x, g of x z, and z. Then you have to get r sub x, 1, g sub x z, r sub z, 0, this is 0, sorry. 0 g sub z 1. And then cross product, then you're going to get, and then magnitude, you're going to get 1 plus f sub x squared, g sub x squared, g sub z squared. You're going to get the same thing in the end. 1 plus g sub x squared, g sub z squared, same way. Okay? So, in example 3, what do you have? Find the area of the part of the paraboloid y equals x squared plus z squared that lies inside the cylinder of x squared plus z squared equals 4. So this is a paraboloid, circular paraboloid. And the projection onto the xy plane is it's a circle. D is a circle. All right? This D. So your D, x, z are the perimeter here. X squared plus z squared is less than or equal to 4. Inside a circle of radius 2. All right? Oh, sorry. Let me just check the video recording. Okay. So here your, and then your y equals x squared plus z squared, right? So this is your g of xz here, all right? So what you need to do here is 1 plus g sub x squared plus g sub y squared. What is g sub x? 2x. G sub z, 2z. So here, in this case, 1 plus 4x squared plus 4z squared. So, what you have to do is, you have to integrate this function, square root of 1 plus 4 of x squared plus z squared, dA. Now, you could try to do this one using xz, rectangular coordinate system. But as you can see, if I draw in here, in xz plane, this is very, let's say z. This is the domain, circle, right? Now, if we use polar coordinate as x equals r cosine theta, instead of y, z equals r sine theta. This can be written as, your domain is from 0 to 2 pi. Then this one can be, your d can be written as what? R is between 0 and 2, theta between 0 to 2 pi, right? Inside the circle, radius 2. So, theta runs from 0 to pi to 2. 1 plus, this is r squared. Right? And then dA becomes, in polar coordinate, r, we did that last time, right? 12.4. dr d theta. Now, r is out. If you call it u equals 1 plus 4r squared, d will be 8r dr. So r dr is 1/8 of du, and this is square root of u. Alright? So this one is now split. It's a separable equation, 2 pi 1 d theta, 0 to r, 1 plus 4r squared, 1/2 r dr, and this is just 2 pi, and this is u to the 1/2, 1/8 du, right? So, u to the 1/2 integral, first of all, 1/8 3/2, reciprocal 2/3. And u, which is this one, to the 3/2. And r runs from 0 to 2. I'm sorry, not r, 0 to 2. Okay? So in the end, it's going to be, okay, 2 to 4, so 2 pi over 6. Pi over 6 times r equals 2, 4, 16, 17, 3/2. 0. 1 to the 0 is 1, just 1. That's the answer. You can write this one as 17 times square root of 17. Alright? So, in the end, this was the main formula of the surface area. When your surface is given by vector equation r of uv. But if it is given as z equals f of xy, 1 plus f sub x squared, f sub y squared, dA. If it is given as y equals g of xz, then same 1 plus, if x equals given as h of yz, then you have square root of 1 plus h sub y squared plus h sub z squared dA. It's the same idea. Alright? Okay, that's the end of lecture of section 12.6. By the way, as I wrote in the email, we don't cover 12.5. We skip the application section of 12.5. So next time, we will do 12.7. Within this week of March 30th, we have to cover up to the first half of section 12.7. All right? All right. I'll see you next time.